Hello everybody, my name is Satoshi Hoshino. I am from Unuma University, Japan. The title of my presentation is End-to-End Motion Planners through Multitask Learning for Mobile Robots with 2D LiDAR. For autonomous navigation as shown in this movie, first off, the robot is required to build a map of the environment. Then the robot plans the paths and motions according to the localization result in the map. In the light mode movie, here you can see the localized position and the planned path. If an obstacle is in front of the robot replans the path or plan the avoidance motion. So in this presentation, we focus on this motion planning in order for the mobile robot to move toward the destination while avoiding obstacles. This is an essential capability for the mobile robot. Motion planning is to determine a motion output AT, which is composed of the linear velocity and angular velocity Vt and omega t for sensor input at time t. In recent years, motion planners based on deep neural networks have been proposed. These deep neural networks are used to determine a motion output for the sensor input. In other words, a deep neural network plays a role of planning policy. So the motion planning is represented as shown in this equation here. We have thus far proposed motion planners based on multi-layer perceptron MLP. Given a 2D LiDAR equipped with a robot, the range data was used as a sensor input. In our previous works, the policies, which is represented by MLP, have been trained through imitation learning. In the framework of imitation learning, first off, desired motions for autonomous navigation, including obstacle avoidance, are instructed. After that, networks are trained so as to determine the instructed motions as the outputs for the sensor inputs. Only a trained policy, which is DNN, lies between the input and output. So these are called as end-to-end motion planners. Here, let us explain the motion planner based on MLP. First off, range data around the robot are measured by the 2D LiDAR mounted on top of the robot, as you can see here. The range data are fed as inputs to the motion planner. According to a localization result, a destination angle and the distance to the destination are fed as an input, as you can see here and here. From the motion planner, the velocity and angular velocity are determined as the output. However, imitation learning sometimes causes a problem of generalization ability of the motion planners. In consequence, it may be difficult for the robot to plan suitable motions in unknown environments. For this challenge, we introduce an auxiliary task into the output layer, in addition to the main task to determine the linear and angular velocities as the motion output. As the auxiliary task, the motion planners estimate the destination angle. Through multitask learning, the accuracy of the main task is increased by the auxiliary tasks. In this presentation, we apply MLP and CNN to the motion planners as the policies. For imitation learning, first off, a supervisor instructs the robot to move toward the goal destination while avoiding obstacles. At the same time, the robot registers the sensor inputs and desired motion outputs instructed by the supervisor. These are used in the training dataset D. The supervisor's policy is assumed to be an optimal. So the robot is instructed to optimally move toward the destination for the sensor input by the supervisor. On the other hand, the policy of the robot in the running phase is represented as you can see, where theta indicates network parameters. Therefore, the network is trained with the following objective function in the learning phase. By repeatedly updating the policy, it approaches the optimal. In doing so, the motion becomes increasingly similar in the ones instructed by the supervisor. Finally, this trained policy is used in the motion planner. Here we propose the motion planners based on MLP and CNN. In this figure, it illustrates a basic structure of the motion planners based on MLP. This motion planner has no branches to the main task without hard parameter sharing, HPS. The range data measured by the 2D LiDAR are directly fed to the input layer. Moreover, destination angle and distance are fed to the first hidden layer. The output layer is composed of two nodes for the main task to determine the linear and angular velocities. By applying hard parameter sharing, the last hidden layer is allowed to have branches. Here, the last hidden layer has two branches to each of the motion outputs as indicated by the red dashed rectangles. In order to improve the generalization ability of the motion planner, we introduce an auxiliary task into the output layer, in addition to the main task. As the auxiliary task, the motion planner estimates the destination angle. In this structure, furthermore, the last hidden layer had three branches to each of the outputs by applying hard parameter sharing. On the other hand, a basic structure of the motion planner based on CNN is illustrated in this figure. While the range data are directly fed as inputs to the motion planners based on MLP, as you can see here, the range data are first stored on one-dimensional array, as you can see here. Through the convolution and pooling layers, range features are extracted from the one-dimensional inputs. For a vanishing gradient problem, two residual building blocks, including shortcut connections, are applied, as you can see here and here. The extracted features are then flattened and further fed as inputs to the fully connected layers. In the fully connected layers, four types of MLP as illustrated above from here to here are applied. For network training, motions desired for autonomous navigation, including obstacle avoidance, are instructed by a supervisor in an environment as shown in this picture. We provided a corridor with a width of 2 meters. In the corridor environment, obstacles are arranged. The robot is allowed to localize the position in the map by using the 2D LiDAR, and the robot is instructed to move from S toward G while avoiding the obstacles arranged in the environment. At the same time, the moving robot registers the destination angle and the distance, in addition to the range data as the inputs. Furthermore, the robot also registers the linear and angular velocities instructed as the desired motion output by the supervisor based on the optimal policy. For multitask learning, the desired destination angle is further given in the output here. Depending on the motion planners with different outputs, the loss is calculated as follows, where LV, L omega, and L phi dot G represent the mean square errors between the outputs from the network and dataset. Finally, the MLP and CNN with the trained network parameters that minimize the loss value are used as the policies in the motion planners. In this experiment, the robot autonomously moves toward the destination while avoiding obstacles in unknown environments. These pictures show the navigation environments unknown to the robot. Compared to the corridor environment, the hole has a width of 7 meters. The arrowed line marked on S here indicates the initial orientation of the robot. In the same hole, obstacles are arranged in different positions. In the first environment, each obstacle is composed of 2 boxes. On the other hand, in the second environment here, these obstacles are composed of a single box. The robot tries to move from the start position S toward G 10 times in total. For comparison, each of the 4 motion planners based on MLP and CNN, depending on the number of outputs and hard parameter sharing, is applied to the robot. As the generalization ability of each motion planner for the unknown environments, we focus on the number of success in navigation. In this table, we compare the navigation result of the robot in the first and second environments, depending on the types of the motion planners based on MLP and CNN. As for the motion planners based on MLP, the number of success in the navigation was increased by estimating the destination angle phi dash g in addition to the main task B and omega. Furthermore, the effectiveness of hard parameter sharing for multitask learning was shown. As a result, the robot based on the motion planner with 3 branches to each of the outputs for the multiple tasks reached the destination 10 times in the first environment and 8 times in the second environment, respectively. In contrast to these results, neither multitask learning nor hard parameter sharing was effective for the motion planners based on CNN. As a result, the robot failed many times regardless of the structure in the fully connected layers. From the navigation results, it was shown that MLP is more effective than CNN for improving the generalization ability of the motion planners. In conclusions, we presented end-to-end motion planners based on deep neural networks. For autonomous navigation in environments unknown to the robot, we introduced an auxiliary task to estimate the destination angle in addition to the main task to determine the linear and angular velocities as the motion outputs. In the navigation experiments, we showed that the generalization ability of the motion planner based on MLP was improved by estimating the destination angle. As a result, the robot successfully moved toward the destination even in the unknown environments while avoiding obstacles. Finally, let us show you the navigation trajectories and the moving robot based on the motion planner of MLP in the first environment. Okay, that's it. Thank you for watching.